this next over it. Oops. Okay, so at Arcus, how many people here know what a white box switch is? Sit on top of it. And I'm actually in the back end. I do protocol design and architecture. And this is actually stuff I'm working on, and it's chugging its way through the IETF and other sausage machines. Okay, so this works. We do this commonly. This might work, but it's starting to get a little edgy, and this won't work. So what do? This works. This is called a Clos network. The CLOS is correctly spelled, only the C is capital. And that's because Charles Clos described it back in '53, Bell System Lab, and it was originally done, Clos networks were done for telco switching. Okay, so what's interesting about this, I bet to this, so what's interesting about this is, you can have standard routings, and then you have layers of switches. These are called spines. These are leafs, and these are top of rack switches. Okay, and IIJ, my other career, built a second medium scale data center with 6,000 racks. Okay, that's a medium scale data center these days. Okay, so how does that work? How do you route in something of that scale? Okay, OSPF is okay to 500 nodes maybe. ISIS is good to 1,000 or so. But they're, aside from the scaling problem, when you have 6,000 racks and the spines and the leaves and the double tours at the top of every rack, so you've got this, which is well beyond this scale. These are also chatty protocols. Okay, they go beep frequently. They're link state protocols. So, hey, this is supposed to work. There we go. So this is your Clos on ISPF or ISIS or OSPF. Anybody here recognize this, by the way? No, one of the world's greatest anime, Miyazaki. But anyway, that's a really basic problem, is the noise. Because when you're running something of that scale, I mean, I have a large data center customer who screamed at us because the box issued 2 DHCP requests instead of 1 when it booted. Okay, they want quiet. Okay, but BGP scales well because its signals only changes. So BGPs become very common in large-scale data centers. Okay. BGP's quiet as the updates are infrequent, but equal cost multipath gets very wide. We see 32, 64, even 128 multipaths that have to be decided. Okay, you do not, oh yeah, every rack is often an AS. Get over it. It seemed silly to me at first, but they're running BGP, they call them each an AS, and it just goes on like that. Okay, but what the heck's the decision process? Do you really want to configure BGP for massive equal cost multipath in something that big? It's disgusting. Okay, even when you have serious automation, this is not something you want to write home to mother about. Okay, so we consult the professor, one of the greatest computer scientists that we've ever had at Dijkstra. He's the father of shortest path first, SPF. Okay, which My monitor just went blank, please. Screens went blank too. Ah, that's nice. So he did shortest path first. Unfortunately, he died a couple decades ago. And I just want to mention this because another great computer scientist in our field in networking died just yesterday, the day before, Sally Floyd, who probably no one here knows. Can we have a little AV here? Is there something I'm doing that could be done better that would make it work? Point at that screen instead of this screen? It's stand on my left foot. Okay, so anyway, Professor Shortest Path first, and we do something called BGP-SPF. It's the path calculation of ISIS and OSPF. In other words, shortest path first with the update rate of BGP. Okay, and the hack is SPF. I thought BGP was path vector, not link state. So we take best path out and we replace it with SPF. It runs Dijkstra instead of best path. Okay, so here's BGP4 Classic. You've got the neighbor distribution, et cetera, the policy. You've got all this big tie breaking stuff. Path length, is it, where did it come from? What order did it come? All these things that are the complex BGP decision process. And you take them out and throw them away, right? And you just put in SPF. Okay, so this is actually, you know, there are versions of this out there. It's still going through the ITF sausage machine. It's pretty easy. The decision processes, phase 1 and phase 2, best path, et cetera, replaced by Dijkstra. Phase 3, the tie breaking can be skipped as the reachability is unique per speaker. And you just have to make sure you only have the most recent NLRI. Okay, it's the peering model is the one you're used to, except how do I find my neighbor? What's the link? I need to discover and assure liveness is the connection to my neighbor in the Clos. Okay, you can do a route reflection hierarchy, and it doesn't have to be fully connected the way you do when you have classic policy, but traditionally we do that anyway because our heads are stuck there, okay? So I just want to point out this paper. I don't fully subscribe to it because it's very centralized, but it's a great classic paper from the Google folk on 4 generations of their Clos designs. Just remember Jupiter Rising, it's simple search will find it. So how does BGP-SPF learn the topology? I don't want to configure it by hand or even automation. So I need to discover my neighbor on the Ethernet. LLDP might work, except it's an IEEE protocol, so we can't hack on it. And it's got, IBM has IPR on anything over 1,500 bytes, which is just disgusting, okay? But and we may want some big PDUs. So we wanted something simple and saw no real need for, you know, reinventing SIS. So we propose a new ether type with type length value PDUs. And we talk about ether payloads. I'm not going to talk about the Ethernet framing because that's boring and the same. So what we've got here is, can people on that side of the room easily see the laser here, or do I need to do both? I'll favor you for a while. what we've got is each one of these is a device, one of these routers, and it's got BGP-SPF at the top talking TCP to its BGP peers. But down at the bottom, there's these Ethernet PDUs are being exchanged and doing discovery. So this guy discovers this girl, and they say, oh, what are your IP addresses just on this interface? And what's on this interface? And then they can push them up to BGP-SPF, okay? And then BGP-SPF can build a topology using shortest path first, okay? But first it has to know the links, okay? So as I said, I can't walk here. Oh, yes, I can. So, oops, oh, there we go, okay. So we have a transport layer up top, which is, this is very like TCP, okay? So there are these multiple of these datagrams. They've got a sequence number and datagram length and checksum, and then the payload, just standard protocol gloop. And you reassemble them, and they can arrive out of order, and they can be dropped and retransmitted, et cetera. And then you can assemble them into a protocol data unit when you've got the whole set for one blob. And these can be pretty darn big, right? Because each datagram can be 24 bits worth. And then you can assemble 24 bits of those. So this can be pretty giant. Okay, so what we really care about is these PDUs. This is just a transport layer to produce the data layer. And yes, this looks like TCP, but we couldn't use TCP because we don't have any IP addresses yet. I can rediscover my neighbor MAC Ethernet address, but I can't tell what her IP address is, so I can't use UDP, TCP, et cetera, et cetera. So we do a cheap TCP-like protocol. We do a reassembly of datagrams, retransmission with backoff, PDUs are acknowledged. When somewhere is late, I'll point to some open source code implementation of this. It's 1,000 lines, the whole thing. All the protocol, and I'm not going to show you much of it, is 1,000 lines of Python, right? Written by a programmer who comments heavily. So we have a fully stateful session per peer, okay? So we do graceful restart, so you can resume a la BGP. So every PDU, every encapsulation, when I want to tell you, here are my IPv4 addresses, it has a serial number. So if we drop this whole session and want to restart, the open can say, hey, the last serial number I got from you was this. Can you restart from there, please? And they can either do that or they can start from nothing. Okay, there's also some authentication keying that can be exchanged, signatures, so that, and these are optional. You can have they want who all say they want security, and when you ask them, I'm also a security person, we say, what's your threat model? They go, huh? So we have put in the ability to have some security against certain kinds of threats, like somebody comes in and does a monkey in the middle attack on your Ethernet. But I don't know what really their threat model is. These data center people, I think, have this fantasy that because it's all within these big cement walls, it's safe, okay? And if you think that's true, you can come hear my talk tomorrow. It's like BGP, it has announce and withdraw. So you can announce a bunch of prefixes withdraw, and that's as the operator configures their interface and adds new addresses or new MPLS labels. Okay, so there's announce and withdraw. You can say, hey, this is my primary address. You can say, hey, this is an underlay and overlay address, and I don't think we want to go down this rat hole, but it's interesting. It could be, this is a loopback address, okay, which of course we're going to want when we move towards BGP-SPF. Okay, there's explicit acknowledge of errors and explicit acknowledge of good load. Okay, so this is the East-West protocol. This is the stuff that gets the addresses. You now know the links. Every device knows its links. It doesn't, remember that protocol doesn't tell you what, doesn't tell this device what this address is, only what it's interfaced, it just has the addressing on the links. Then it pushes it up. There's also a liveness thing, or keep alives, et cetera, so you can ensure the links are hot, or you could use BFD, okay? You package it up, okay? And there's BGP-LS, which is, I won't go into it, I don't approve of it, but it has a way of packaging this stuff up and giving it to a BGP protocol. So we use just a teeny bit, two PDUs from 7752 BGP-LS, hand it to BGP-SPF. Now this BGP-SPF knows the links to the left and the right. Somehow, magically, and we'll get to it in a minute, it can talk to this neighbor, who can talk to this neighbor, and now they exchange this link information, and each one of them can build a picture of the total topology. Okay? So, as I said, you just repackage it up and hand it to BGP-SPF. But how does BGP-SPF start? I really don't want to configure all that stuff. As I said, if anything, I am lazy. Okay? So we don't want to configure it. Why not add a PDU or two to this link state protocol to pass BGP configuration info? Okay? So it might be, I do not want to assume that the upper layer protocol is BGP. So one of the things we'll have is, what is the upper layer protocol type? And then a bunch of attributes. Okay, for BGP, I want to provide the minimal set of configuration parameters for the open to succeed. There are BGP discovery protocols, when you look at them, they have 30,000 parameters, but I don't understand, none of these proposals have flown or been implemented. But what happens if some of those parameters conflict with the ones that BGP Open discovers? You know, you've got the real problem, the classic problem of data in two places. So we're going to only exchange what is the absolute minimum necessary to open the BGP session. So you don't want multiple sources of truth. So what you've got is my ASN, my v4 peering address or v6 peering address, okay? And the prefix length, of course. And if you have any MD5 gloop, that's all you need to open a BGP session. The rest, it's exchanged by open. So now these devices discover each other at layer 2, push the stuff up, let BGP form the associations, then BGP-LS forms the topology, and you're good to go. You people have the British idiom, Bob's your uncle? Yeah, and Bob's your uncle. That doesn't work well in the States, by the way. Okay, so BGP can open it up and that will exchange all the rest. There's running code for this. There's open source Python 3 for an earlier version of it. There's Golang source that's for the exact current version, and I hope to get this opened up soon. And there is no IPR in any of these proposals. And that's all she wrote. And this is what this is kind of what I do in one half of my life, is design this kind of glorp, right? And I can tell you about routing protocols, et cetera, but this is actually fun. I get to try to put it back together. I've been getting in trouble taking things apart since I was 3. There you go.
Thanks, Randy. Thank you, Randy. Yeah, any questions? 2 mics on this, either side, or 1 mic on either side? I have no idea how this thing works. How are you passing it? Maybe I'll just take it out as well. Randy, I think you broke the mic. There we go. There we go. Great. Thanks for that, Randy. Great. So the last talk for the day, but certainly not the least, is one of our friends from Germany, Mr. Thomas.